Hi all. So welcome to another video of linear control system based on the KTU syllabus. And in the previous videos we were discussing about the Bode plot problems. So here also in this video we are going to discuss a problem, that is a Bode plot problem. Okay. So the question is, sketch the Bode plot for the following transfer function and determine phase margin and gain margin. And our function is g of s equal to 75 into 1 plus 0.2s by s into s square plus 16s plus 100. Okay, so this is our function, and we know that by observing the function there are terms, that is a first order term is in the numerator and a second order term is in the denominator, and another term is 75 by s. Okay, another term. So when comparing with the first order and second order terms, okay, the change is that for the second order term the corner frequency, okay, that is omega c, will be its natural frequency omega n. Okay, so actually we have to find the natural frequency of the second order function, and it will be its corner frequency. Okay, the corner frequency is nothing but, we know that at the corner frequency there will be a change in the slope. Okay, that is this particular frequency will be the corner frequency. Okay, if you are drawing the magnitude plot up to this frequency, there is a particular slope, that is something, it is 0, and after that frequency the slope changes to minus 20 or something like that. Okay, so that's our corner frequency that we know. So first we have to find that. Okay, so for finding the natural frequency we have to compare with the second order term with the standard term, that is square plus 2 zeta minus plus omega n square, that we know. So by comparing with, we will get the omega n as 10, because omega n square equal to 100 here, so omega n will be equal to 10, and the value of zeta, that is damping ratio, is also 0.8 here. Okay, by comparing. And after that, the next step is to convert the given function into the standard form, that is standard Bode form. Okay, so for converting it into standard Bode form, we have to make all the first order terms into this form, that is 1 plus st form, and also we have to make the second order term also something like 1 plus or 1 minus, like that. Okay, so that is the standard form. So for here the first order term is also in the standard form, that is 1 plus 0.2s, and the second order term here it is s square plus 16s plus 100. Okay, it is not like 1 plus or 1 minus form. So for making that, we are taking outside this 100, so it becomes 100 into s square plus s square by 100 plus 16s by 100 plus 1. Okay, so this 75 by 100 we know it as 0.75. So the function becomes 0.75 into 1 plus 0.2s by s into 1 plus 0.01 s square plus 0.16 s. Okay, and after that we have to write the sinusoidal transfer function. This function is in s domain. Okay, so by substituting s equal to j omega, okay, s equal to j omega, we have to write the sinusoidal transfer function. Okay, so 0.75 into 1 plus 0.2 j omega divided by j omega into 1 plus 0.01 j omega square plus 0.16 j omega. Okay, so here we know that this j omega square becomes, okay, the j omega square becomes it is j square is minus 1, we know, so the term becomes 1 minus 0.01 omega square plus j 0.16 omega. Okay, and after that we are doing our normal procedure, that is we have to first draw the magnitude plot. We have to first calculate the terms for magnitude plot. So for calculating the magnitude plot, we have to first find the corner frequencies. Okay, the corner frequencies here are, we know that the corner frequencies will be there for first order and second order terms. Okay, so here the first order term is 1 plus 0.2 j omega, and we know that for finding the corner frequency for the first order term, we have to find the reciprocal of the coefficient of j omega, that is reciprocal of this 0.2, that is 1 by 0.2. We will get it as 5 radian per second. And the second order function here it is this one, and we know that the corner frequency will be its natural frequency omega, that is omega c2 equal to omega n equal to 10. Okay, and we have to write the corner frequencies in the order such that in the increasing order of the corner frequency, that is omega C1 will be 5 and omega C2 will be 10. Okay, and after that we have to construct the table. In that we have to write the terms in the increasing order of its corner frequencies. Okay, so from the function we know that there will be 3 terms. Okay, one will be this 0.75 by j omega, another will be 1 plus j 0.2 omega, and another one is 1 by 1 minus 0.01 omega square plus j 0.16 omega. Okay, so we know that for the term 0.75 by j omega there will not be any corner frequency, so we will write that first 0.75 by j omega, and second term is 1 plus j 0.2 omega, and another one is 1 by 1 minus 0.01 omega square plus j 0.16 omega. So don't forget to write the third term as 1 by 1 minus 0.01 omega square plus j 0.16 omega. Okay, 1 by is there because it is in the denominator part. Okay, and we know the corner frequencies are 5, 10, and we have to find the slope. Okay, so for the first term, the omega term is in the denominator, so the slope will be minus 20, and the second term it is in the numerator, that is 1 plus j 0.2 omega is in numerator, so the slope will be 20, and the third term is a second order term, and it is also in the denominator part. Omega square is in the denominator part, so the slope will be minus 40. Okay, and for finding the change in slope, we have to add the first 2 terms, that is minus 20 plus 20, we will get just 0, and for finding the next change in slope, we have to add this 0 with minus 40, that is cross. We have to crossly add the 2 terms, that is 0 and minus 40, we will get as minus 40. Okay, and after that we have to choose some lowest frequencies and highest frequencies, that is omega L and omega H. So here we are taking omega L as 0.5 and omega H as 20. Okay, that is omega L must be less than omega C1 and omega H should be greater than omega C2. Okay, so we are having 4 frequencies now, that is omega L 0.5, then omega C1 5, omega C2 that is at 10, and omega H it is at 20. Okay, you can also choose the value of omega H as 30, 50 like that, no problem. Okay, but the value of omega H should be greater than this omega C2, that's all. Okay, and after that we have to find the corresponding gain values for all these frequencies. Okay, so first we are going to find the gain value for this omega L. Okay, we know that the equation for gain, there is gain in decibel, A is equal to 20 log mod. In the modulus value we have to write the first term, that is 0.75 by j omega, 0.75 by j omega, and the omega value is omega L, that is 0.5, so 20 log 0.75 by 0.5 we will get as 3.5. This is 3.5 decibel, 3.5 decibel. Okay, and the second term we have to find the corresponding gain for the second frequency also, that is here the frequency is omega C1, that is 5. Okay, we have to use the same equation for the first 2 frequencies. The equation is same, that is 20 log mod 75 by j omega, so we will get as minus 16.5 decibel, and from the third frequency itself the equation is changing, and the equation is the gain at omega C2 is equal to slope from omega C1 to omega C2 into log omega C2 by omega C1 plus gain at omega equal to omega C1, that is gain at the previous frequency. Okay, so slope from omega C1 to omega C2. Okay, so here the slope from omega C1 to omega C2 is 0 here. Okay, 0, so we are adding that 0 here into log 10 by 5 plus gain at previous frequency, that is minus 16.5. Okay, so we will get it as omega at omega equal to omega C2 the gain is minus 16.5, the same gain, and at omega equal to omega H slope from equation is A equal to slope from omega C2 to omega H log omega H by omega C2 plus gain at omega equal to omega C2. So the slope from omega C2 to omega H, it is minus 40, that is second term in the change in slope column. So minus 40 into log 20 by 10 plus gain at the previous frequency. The previous frequency is omega C2, that is minus 16.5 here. So we will get us minus 28.5. So we are having 4 frequencies here and 4 corresponding magnitude values here. Okay, so it is enough to plot the magnitude plot. So the next we have to plot the phase plot. We have to calculate the values for phase plot. Okay, so for that we have to write the equation, that is phase angle equation. So the g of j omega term is this one, that sinusoidal transfer function of g of j omega is this one, and we know that we can find the we can start writing the angle from the numerator part itself. Okay, so here in the numerator part we are having a first order term, and we know that the phase angle is the tan inverse b by a. Equation is tan inverse b by a, so tan inverse what is 0.2 omega by 1, that is tan inverse 0.2 omega. Okay, and the another term is where is a 0.75 j omega, so the j omega is in the denominator, so the angle will be minus 90, and second order term is also in the denominator. So here we can also treat the second order term as a plus jb format, because here this 1 minus 0.01 omega square is a real term and 0.16 omega is an imaginary term. Okay, so tan inverse b by a. Okay, so here b is 0.16 omega, a is 1 minus 0.01 omega square. Okay, so you can see here that is tan inverse 0.16 omega by 1 minus 0.01 omega square. Okay, that is the angle of the second order term, and also it is in the denominator part, so the sign is minus. Okay, and this is the corresponding phase angle, tan inverse 0.2 omega minus 90, then minus tan inverse 0.16 omega by 1 minus 0.01 omega square. Okay, so here you can see two phase angle equations, because there will be two parts for this phase angle equation based on the frequency. So for any function, okay, if there is a second order term, in the function, so we have to choose the phase angle equation phi equal to this one for a frequency omega less than or equal to omega n, that is omega n, here it is 10 omega, we know that omega c equal to omega n equal to 10. So up to that 10 radian per second we have to consider the phase angle equation as this one. Okay, and for frequencies greater than omega n, that is greater than 10 radian per second, the equation becomes this one, and the change in these two equations is that we are adding a plus 180 with the corresponding with the phase angle corresponding to the second order term. Okay, that is the phase angle corresponding to the second order term is this one, so we have to add a plus 190 with that term for frequencies greater than omega n, that is for frequencies greater than 10 radian per second. The reason here is because in quadratic factor, that is the second order term is a quadratic term. Okay, so in quadratic factors the phase varies from 0 to 180 degree, but in our normal calculator, that is in our scientific calculator, the calculator calculates tan inverse only between 0 to 90 degree. So hence a correction of 180 should be added to phase after omega n. Okay, so after omega n we have to consider this equation, this phase angle equation. Okay, so we have to construct the table for different values of omega. So we are choosing some different values of omega, 0.5, 1, 5, 10 like that. Okay, up to 100, and based on this value of omega we have to choose the angle phi. Okay, here you can see clearly that is for omega value less than or equal to 10, that is up to 10, we are using the first equation. Okay, and for a frequency value of 20 the equation becomes this one, that is we are adding a plus 180 term with the second order term. Here the second order term is this one. Okay, so we are adding a plus 180 with that term, so the actual angle here is 133.2 instead of this minus 46.8. Okay, so while calculating the entire phase angle we have to consider this 133.2. Okay, so this is the corresponding phase angles for different values of omega. Okay, and after that we have to plot the magnitude plot as well as the phase plot. Okay, so here the magnitude plot is plotted between the value omega for different values of omega. In the y-axis we are taking the gain in decibel. Okay, so here the range is from 3.5 to minus 28.5, that is minus 28.5 is the less than 1, and up to 3.5 we have to choose the scale. Okay, so here you can see in the x-axis the top value we are taking it as 10. Okay, 10, then the next dark line means 5, then 0, minus 5, minus 10, minus 15, minus 20, up to here the minus 28.5. Okay, so here we are taking up to minus 30 or minus 35 something. Okay, we are taking the scale. Okay, and in the for phase angle plot we have to choose the x-axis is same, that is omega. In the y-axis here we are drawing an y-axis here. Okay, that is for not coinciding these two terms, we are actually drawing the y-axis here for phase angle. Okay, and for phase angle also, the phase angle, we know that the phase angle varies from this minus 88 to minus 174 something. Okay, so here the last values we are choosing is minus 180, then minus 170, minus 160, like that we can increase the values. Okay, up to 0 we are plotting, and after that for each value of omega we have to plot this magnitude plot and the phase values. Okay, and the magnitude plot, after plotting the points, we can use the scale for continuously drawing the graph, and the phase angle plot is only drawn by freehand. Okay, don't use scale for connecting different points. Okay, we have to draw the lines by connecting all points by freehand. Okay, so this is the corresponding Bode plot. This is the magnitude plot and this is the phase plot. Okay, and from these plots we have to find the phase margin as well as the gain margin. Okay, so listen carefully. For finding the phase margin, equation is, that is gamma is the phase margin. So for finding the phase margin, equation is 180 plus 5gc. 180 plus 5gc. This 5gc is the phase angle corresponding to the gain crossover frequency omega gc. Okay, omega gc, and this omega gc is the frequency at which the magnitude of our function becomes 0 decibel. 0 decibel. So that is, which means in our graph we have to find a point where this magnitude plot becomes 0 decibel. That is, in this graph it is clear that at this point the magnitude becomes 0. That is, this line crosses this 0 decibel. Okay, so the frequency corresponding to that point is omega gc. Here you can see it is omega gc, that is approximately 6.7, that is in between the 6 and 7 you can see the cross point, that is 6.7 or 6.8, like. Okay, so that is our omega gc. Okay, and for finding the 5gc, the 5gc is the phase angle corresponding to this omega gc. Okay, that is, this is omega gc, that is 0 decibel, corresponding to that point is omega gc. So for finding the phase angle corresponding to omega gc, we have to extend this line to phase plot and we have to find the corresponding 5gc here. So here from this graph, this 5gc is minus 88. Okay, minus 88. So for finding the phase margin gamma, the equation is gamma is equal to 180 plus 5gc. So 5gc is minus 188. Sorry, minus 88. So 190 minus 88 becomes 92 degree. So 92 degree is the phase margin. Okay, so and for finding the gain margin, okay, for finding the gain margin, actually we have to check whether our phase plot crosses the minus 180 degree. Okay, minus 180 degree. Okay, so for finding the gain margin, we have to first find the corresponding frequency where the phase plot crosses minus 180 degree. Okay, so that frequency will be phase crossover frequency omega pc. Okay, omega pc, that is at omega pc the phase angle of our function is minus 180 degree. Okay, so that is, we have to observe the phase plot clearly, and at what point this phase plot crosses minus 180 degree, and that frequency corresponding to that value is the phase crossover frequency omega pc. Okay, and suppose, okay, in our graph, suppose this 10, okay, this 10 is, it is not that omega PC here. Suppose just assume this 10 as our omega PC. Okay, 10 as our omega PC. Okay, then for finding the gain margin, we have to find the decibel magnitude corresponding to this 10 radian per second, that is this one. Okay, we have to extend the line, so it will meet at some point in the magnitude plot, and we have to find the corresponding our corresponding gain value. Okay, so here it is approximately minus 16.5, that is minus 16.5. Okay, so the gain margin will be negative of this minus 16.5, that is plus 16.5 will be the gain margin. Okay, which means that is we have to find the omega PC first. Omega PC we can find from this graph, that is the phase plot crosses minus 180 angle. The frequency corresponding to that will be omega PC, and at omega PC we have to extend the line to the magnitude plot, and we have to find the corresponding decibel magnitude, and the negative of that value will give the gain margin. Okay, so here if you are observing the graph, that is we know that if you are increasing the frequency, okay, that is 50 above that 20, we are increasing the frequency 50, 100 like that, but the value of phi is not reaching minus 180. That is if you are choosing the omega as 200 here, okay, 200 here, then also the value of phi, okay, will not reach the value minus 180. That is something, the value will be something below this 170, that is 180, that is approximately 178 something. Okay, something like that. Okay, that is it will never reach us, whatever may be the frequency, it will never reach us a value minus 188. Okay, so you can check by finding the phase angle, okay, using the calculator itself. Okay, so we are assuming that the phase plot meets the minus 180 degree, that is the phase plot crosses the minus 180 degree angle at infinity. Okay, at infinity frequency, okay, and at infinity frequency the corresponding the decibel magnitude will be minus infinity. Okay, that is the mod g of j omega value. Okay, decibel magnitude means that is mod g of j omega value. Okay, it will be minus infinity. Okay, that is here once again I am saying that we are assuming that the phase plot crosses minus 180 degree at infinity frequency, that is it is increasing. If you are increasing the frequency, okay, the graph will be something parallel to our x-axis. Okay, it will go like that, it will never reaches up that minus 180 degree. Okay, so we are assuming that if it will reach minus 180 degree at infinity frequency. Okay, so if the frequency is increasing, we know that this graph, okay, this line is also extending to downwards. Okay, downwards, that is the corresponding decibel magnitude, the decibel magnitude corresponding to infinity frequency will be minus infinity, that is the value, that is the gain. Here it is decreasing, that is like minus 40, minus 50, minus 100, like that. It will increase when frequency increases, it will decrease when frequency increases. Okay, so we are assuming that the corresponding decibel magnitude, okay, decibel magnitude is minus infinity. Okay, so minus of minus infinity, that is minus of minus infinity, we will get as infinity. So infinity will be the gain margin. So here the gain margin will be infinity, that is plus infinity. Okay, so you can read these points. Okay, it is clear that the gain margin is plus infinity. Okay, so I hope it's clear. So thank you.